It's important to actually know your pKa values so you know which acid is stronger than another acid, but we'd really like to understand the structural basis for the greater acidity of some acids versus others. And you would have discussed the structural basis for differences in acidity in your dental chemistry class. And you probably learned 3 of the 4 major things that we look at when we're determining relative acidity. But you will not have learned the 4th because it didn't apply to the molecules we talked about in dental chemistry. The main things in approximate order of importance are resonance, a larger number of resonance structures, results in a more stable anion. And when we're talking about acid strength, we're really talking about anion stability. Because in all cases, the cation is H plus or H3O plus if you're in aqueous solution. So the difference is really in the structure of the anion. So resonance is one way to stabilize an anion. Another way to stabilize an anion is polarizability. A larger, more polarizable atom can spread out the negative charge more. And the more you can spread out the negative charge, the more stable the anion is going to be. In the case of resonance, you're actually spreading it out onto more than one atom. That's better than being able to spread it out in space, but still associated with only one atom. But still, a larger, more polarizable atom can spread that negative charge out better than a smaller, less polarizable atom. Remember that the goal of an electron is always to occupy all space simultaneously. So anything that spreads out that electron and allows it to go more places is going to stabilize it. So we have resonance and polarizability. We also have electronegativity. The more highly electronegative atom holds its electrons tighter. Generally, it has a bigger nucleus. That's why it's more electronegative. Right? And when I say bigger, I mean more positive, not bigger in size, volume. So if you have a more positively charged nucleus, you have a stronger Coulomb force that's holding those electrons more tightly. That's better. It stabilizes. We'll have learned about all 3 of those, maybe not in the terms of resonance, polarizability, and electronegativity as the key words, but you will have learned about these things causing differences in acidity. What you will not have learned, the last one, is what we refer to as the S character. An sp orbital, which is 50% S character, smaller than an sp2 orbital, 33% S character, which is in turn smaller than an sp orbital, the smaller the orbital, the closer the electrons are to the nucleus. And the closer the electrons are to the nucleus, the more Coulomb interaction there is, and the more stable the charge is. More orbital. Because the force of attraction is proportional to Q plus Q minus over d squared. So if you decrease d, you increase the force of attraction. The electrons get more tightly. It's similar to what's going on with electronegativity. If you have a larger nucleus, you've just increased Q plus, which means you've increased the Coulomb force of attraction and stabilized the negative charge. If you decrease the size of the orbital, you've increased the force, because it's an inverse relationship between the distance that the electron is from the nucleus and the force of attraction. So this is a new one. This is going to be how we explain why the alkyne is significantly more acidic than the alkene, and the alkene is somewhat more acidic than the alkane, because in an alkyne, we're looking at an sp orbital where that negative charge is. In the alkene, we're looking at an sp2 orbital, and in the alkane, we're looking at an sp3 orbital. So let's take these one at a time. Now, resonance, polarizability, electronegativity, and S character affect the relative acidity of hydrogens in different functional groups. So you know that sulfuric acid, H2SO4, this looks like that. Is a strong acid and is completely dissociated in water. Sulfuric acid is also a liquid, and we write just a one-way arrow that tells us hydrogen sulfate anion also known as the bisulfate ion exists along with the inorganic. And we know that acetic acid weak acid reacts with water to form the acetate ion, but not fully dissociated. And we know that the pKa of carboxylic acid is on the order of 5, and we know that the pKa of sulfuric acid is around -3. So there's about an 8 order of magnitude difference, right, with the sulfuric acid having a pKa value that's negative and is completely dissociated, and the acetic acid having a pKa that's positive, and therefore actually mostly acetic acid in solution. And we know that the reason for that is the difference in stability between the hydrogen sulfate ion and the acetate ion. The hydrogen sulfate ion is more stable than the acetate ion. We can understand that in terms of the larger number of resonance structures that you can draw for the hydrogen sulfate ion, which has three equivalent resonance structures that allow us to delocalize that charge and spread it evenly over the 3 oxygens that don't have hydrogen attached to it. We could, in fact, if we wanted to, have written that as a resonance hybrid. It shows that we have a partial pi bond to each of those 3 oxygens. And we have 2 additional lone pairs on the 2 oxygens that are not partially, that are not double bonded in the individual resonance structure. Acetate ion is also stabilized by resonance, but acetate ion only has 2 oxygens to spread the charge out, it has two equivalent contributing resonance structures and can be written as a resonance hybrid. With fewer oxygens to spread the charge out means that the anion is less stable. In general, the more resonance structures, the better. You're going to increase your acidity by increasing the number of resonance structures. And resonance is usually the most important effect, generally speaking. Not in all cases. There are cases where something will have multiple resonance structures, but none of those resonance structures are particularly stable. And they might be less acidic than something which is highly polarizable. But as a general rule, resonance is one of the most important effects for increasing the acidity. And resonance is also the reason why the hydrogen attached at an allylic position is more acidic than the hydrogen that's not attached to an allylic position. So if we consider propene versus propane, and we dissociate this, because there is a pi bond adjacent to the anion derived from propene, we can actually move that pair of electrons, move that pair of electrons like this, and create a resonance structure that spreads that charge out onto the other carbon. And that's not possible for propane. Thus, the pKa of the propane hydrogen is on the order of 50, and the pKa of the propene hydrogen is on the order of 40. The additional resonance structure, and those are two equivalent contributing resonance structures. A resonance hybrid could be drawn. It has charge spread out onto two ends. Presence of that additional resonance structure drops the acidity by approximately 10 orders of magnitude. You'll see the same thing, but to a greater extent, for hydrogens that are attached to a carbon-oxygen double bond. We use an aldehyde as an example here. So this will dissociate to form an anion. The anion is adjacent to a pi bond. Anytime you're adjacent to a pi bond, it's possible to push those electrons out. But in this situation, ethanol, the two resonance structures that we've drawn are no longer equal contributors. This is a much more important resonance structure, because this one allows the negative charge to go onto the more electronegative oxygen as opposed to the less electronegative carbon. And that drops the acidity by quite a bit more, so that we see a pKa for the hydrogen adjacent to the carbon-oxygen double bond of closer to 20, which is 20 orders of magnitude more acidic than being next to a carbon-carbon double bond, and 30 orders of magnitude more acidic than not being next to a double bond at all. So it's a major, important effect. So those are the functional groups for which resonance is important. Polarizability is mainly important when you're talking about putting a negative charge on an atom that's in a different row of the periodic table. So we can use polarizability to explain the difference in acidity between HI, HBr, and HCl. I'm going to write the most acidic on top. They're all strong acids in water, but hydrogen iodide is a stronger acid, pKa of -10. is a strong acid in its own right, you would actually see a greater dissociation of hydrogen iodide versus hydrogen chloride. And what we're comparing here is the relative stability of the chloride ion and the bromide ion. And I'm probably exaggerating the size. And the iodide ion. And the iodide ion is much larger, which means that this negative charge is spread out over a much larger volume of space. And it's more polarizable if you bring a charge of the electron cloud to be more free to move back and forth, and that also stabilizes the ion. So the larger the ion, the more the charge spreads out in space, and the more the charge spreads out in space, the better. And you know that HF is in fact not even a strong acid. It doesn't have a negative pKa. Its pKa is on the order of 4, roughly, 3-ish, 3 to 4. I think it's closer to 3 than 4, in fact, right? So it's a weak acid. It's not polarizable. The fluoride ion is very small. The electrons are held very tightly, and the lack of polarizability causes that fluoride ion to be a pretty decent base, and therefore HF. Polarizability definitely explains the trends in the hydrogen halides. Polarizability also explains the greater acidity of a thiol. Thiol, which has a pKa on the order of 10. One of the more acidic of the thiols, usually we say about 12 for most thiols, versus methanol, which has a pKa of around 15. Right? Methanol. And that's because oxygen is in the second row. It is a relatively small anion, holding its electrons pretty tightly, but not allowing them to spread out very well, whereas sulfur is a much larger atom, has greater polarizability, allows those electrons to spread out over a larger region of space, and that results in a pKa value that's somewhere between 3 and 5 orders of magnitude more acidic. Right? The difference between methanol and methanethiol is analogous to the difference between HF and HCl, because oxygen is 1 to the left of fluorine and sulfur is 1 to the left of chlorine. So when you're talking about elements in the same group column, but different periods, row, polarizability is generally the important reason why one is more acidic than the other. Electronegativity, by contrast, is most important when you're talking about atoms that are of similar size, or sorry, anions that are of similar size, but nuclei that are of different charges. So generally, you're going to use electronegativity as the argument when you're talking about things that are in the same period, the same row, but different groups. So HF is a stronger acid, for example, than H2O, and H2O is a stronger acid than NH3, and NH3 is a stronger acid than CH4. Right? As we go across the second row from right to left, from fluorine to oxygen to nitrogen to carbon, right, we gradually decrease the number of protons in the nucleus. So F minus is the more stable anion versus hydroxide, which is a more stable ion than NH2. Which is known as the amide ion. Not to be confused with the amide functional group, which is a carbon-oxygen double bond next to a nitrogen. And methyl anion is particularly unstable. So decreasing acidity, decreasing stability of the anion, pKa of HF, as we said, is on the order of 3, pKa of water is on the order of 15, pKa of ammonia is on the order of 35, and pKa of methane is on So those are large differences in acidity as you go from the larger nucleus holding the electron more tightly in the fluoride ion to the smaller nucleus, smaller charged nucleus, holding the electrons less tightly in the case of carbon. And you'll see that same trend in the third row. So you'll see that H2S is a stronger acid than PH3. But H2S is a considerably weaker acid than HCl, right? HCl is an actually strong acid, fully dissociated. H2S, the Ka value, the first Ka value of H2S is on the order of 10 to the minus 8, right? Whereas for HCl it's 10 to the 8th, and PH3 is even smaller. Again, same row, right? These are the third row, these are the second row. Electronegativity stabilizes the anion. So fluoride is a more stable anion than hydroxide. Hydroxide is more stable than H2. Polarizability, when you're talking about different periods, same group. Electronegativity, when you're talking about same period, different group. And then finally, as we already talked about, if we compare ethane to ethene, to ethine, anion. This is an sp orbital. This is an sp2 orbital. This is larger. And this is an sp3 orbital. This is even larger. The smaller the orbital, the more tightly the electrons are held to the nucleus, the more stable. And so your Ka value, your pKa value rather, goes from 25, 40, 44 to around 50. That's S character. Greater S character, more significant.